course, primarily quantum optics, and quantum simulations of condensed matter and high energy physics systems, also nano and quantum photonics, largely under the canopy of quantum information processing. So today, Dr. Amit Rai will talk about propagation of non-classical light through two-dimensional photon lattices. Dr. Rai, can you please take over?
Oh, thank you, Professor Lakshmi Bala, and I would also like to thank you, Professor Amit Rai, for giving me the opportunity to present the work here in QIQT-2022. And I remember that I was also part of QIQT-2021, and we had some very good talk, and so I hope that that tradition will continue. So today I will talk about our work on propagation of non-classical light in circularly coupled arrays. So let me just share the screen. Can you see the screen?
Yes, we can see the screen. Yeah, we can see the screen.
Is it full?
No, it's not full.
Yeah, it's not. Now I think it will.
Yeah. Okay.
Yeah. So I will talk about our work on transfer of non-classical light in circularly coupled waveguide arrays. So here is an outline of the talk. So I will start with the introduction about the optical waveguides in general. So there has been a lot of work related to one-dimensional waveguide arrays, and they have found application in quantum information processing. Then we look at the circularly coupled waveguide array, which have been studied for application in switching and coherent transfer of light. So we consider this circularly coupled waveguide array and look at the possibility of transfer of non-classical features and quantum states of. So we also look at the possibility of perfect transfer of quantum state, and so I'll describe the case where the perfect transfer of quantum state is possible, and then we conclude our talk with important implications. So one-dimensional waveguide arrays, they are a very important elements in classical optics, but recently they have also started to find application in the generation of, for example, quantum entanglement. They are also useful for the study of quantum walk and quantum computation. In addition to these applications, these optical waveguides have also been studied in the context of quantum state transfer. So it has been shown that the perfect transfer of light is possible in case of a special kind of lattice, which are known as JX photonic lattice, which involves modulated coupling. And if you consider these kind of lattices, then it is possible to perfectly transfer light from one side to other. So it has been shown that in these JX photonic lattices, it is possible to transfer the light, but it turns out that it is not possible to transfer the quantum states such as the squeeze state and the coherent state in these JX photonic lattices. So these, why they are interesting, why these waveguides are interesting, because they have they can be fabricated with very low loss, and they can also be fabricated using the femtosecond laser writing technique, which generates waveguides which are very stable. So this is a very important property as long as we are considering the application in quantum information science. So in addition to one-dimensional arrays, one can also consider circularly coupled arrays. So these waveguides are arranged in a circular configuration. I will show the figure for this circularly coupled arrays. So these circularly coupled arrays, they find application in classical optics in terms of power switching, power devices, and coherent transfer of light. So what we are interested to do is we want to consider this circularly coupled waveguide arrays, and we want to see whether there is transfer of non-classical features and quantum states possible in these systems. So quantum state transfer and perfect state transfer and transfer of non-classical features, these are important for application in quantum processing, quantum information processing, and quantum computing. And the quantum state transfer has been studied in not only in optical system, they have also been studied in other kind of systems. For example, in superconducting qubits also. So this and in addition to that, you can also consider this cavities also and study the quantum state transfer. So this quantum state transfer has been studied in a variety of physical systems. So here we look at this possibility of state transfer for circularly coupled optical waveguide arrays, and we consider the non-classical state of light, such as single-photon Fock state, two-photon Noon state, single-mode squeeze state, and two-mode squeeze state as input to these lattices. So all these single-photon Fock state, two-photon Noon state, and single-mode squeeze, these are very important examples of non-classical states of light, and they found a lot of applications in, for example, in metrology and quantum communication and quantum computation also. So here is the system that we consider. So we have these waveguides which and light can propagate in the z direction, and these waveguides are coupled through. So the coupling is considered to the nearest neighbor waveguide. So we consider the coupling to nearest neighbor only, and you can give a single input, or you can also consider a multiple input. But in this figure, we have just shown the single input, but it is also possible, and we'll consider the case where you can give multiple input. And then light can propagate in the z direction, and in the output, you can detect the light, and you can look at different kind of observables. So I will describe what kind of observables one can look at. So here is the Hamiltonian for the system, and so here these waveguides, as I said, they are coupled to their nearest neighbor, and this first side is coupled to the nth side because of this circular configuration. So with this Hamiltonian, we can write corresponding Heisenberg equation.
There seems to be a problem. Can anybody hear the speaker?
Yeah. Yes, we can hear.
Yeah.
Okay, so can I continue? Okay, so here we have written this Heisenberg equation of motion. So if you consider this first side, it is connected to the second and nth side, and then each of this kth side, which is between this first and nth side, they are connected to the k plus 1th and k minus 1th side, and these modes they satisfy this commutation relation, and J is the nearest neighbor coupling constant, and J is dependent on the distance between these sides. And as you increase the distance, the coupling will decrease. And if you place these waveguides close to each other, then the coupling will increase. And here we are only considering the nearest neighbor coupling. So the problem that we are considering is you consider the input state, let's say in the first site, or you can consider any other site. You consider the input in the ith site, and then we look at whether it is possible to transfer this quantum state and non-classical features to the other sites. So we are interested in studying the transfer of non-classical features as well as quantum state. And we also want to investigate whether it is possible to perfectly transfer the quantum states from one side to the other. So as I said, we are considering the non-classical states of light. So first we consider the single photon Fock state that is given by this. Then we consider the noon state, which is an example of a maximally entangled quantum state. So here we have specifically considered two-photon noon state. So this noon state is an entangled state where you have a two-photon in one mode and zero photon in the other mode. Then next state that we consider is the single mode squeezed state, which has this form. We also consider two-mode squeeze state, and this two-mode squeeze state is an example. Is again an example of an entangled state, and these two-mode squeeze states are very much important for applications in quantum metrology and other kind of applications such as quantum communication. In addition to these non-classical states, we also consider coherent state. So that is given by this equation. So coherent state with amplitude alpha, and so we consider this whether it is possible to transfer the coherent states from one side to the other. So when we inject light in the input side and then we look at the output, so then we can look at various quantities. So you can look at, for example, so you can verify the state transfer by looking at this quantity, which is known as fidelity. So here what we are doing is that we are comparing. So we are starting with quantum state in one of the input side, and then we are letting it evolve. And then we are asking the question that whether this quantum state is perfectly transferred to the other side. So what we are comparing here when we are calculating the fidelity is that psi z is the evolved state that from the input state psi 0, let's say, and psi is the given state. So if the perfect transfer take place, then for example, if I consider a single photon input in the first side and I'm asking the question that whether it can be transferred to the third side, then this side will represent the single photon input state in the third side. So we are looking at this quantity fidelity, and if this quantity becomes 1, then we can say that there is perfect state transfer. In addition to that, we also look at the transfer of mean photon, which is given by this equation. In addition to these two quantities, we are also looking at, when we consider the squeeze state, we are looking at the evolution of the squeezing parameter. And we are asking the question whether, so squeezing is a non-classical effect. And we are asking the question that whether this non-classical feature can also be transported from one side to the other. So here we are considering these two these two quantities. One is fidelity and another one is photon number. So one thing that that is important to notice here is that it may be possible that light is transferred from one side, light is completely or perfectly transferred from one side to the other, but the quantum state is not perfectly transferred. So that is the reason why we are looking at the evolution of the mean photon number as well as the fidelity. So only when the fidelity becomes 1, we can say that the quantum state is transferred. So when I show the results, then we'll see that it is possible. It is very much possible in some cases that the light is transferred. So there is a perfect transfer of or complete transfer of mean photon number from one side to the other, but the quantum state may not be perfectly transferred. So it is important to consider both these quantities as we'll show in the later slides. So as I said that we are considering these important non-classical states of light. For example, single photon Fock state, two photon noon state, and coherent state in circular waveguide arrays. So let us consider the simplest case first. So let us consider the simplest case where you have a single photon, where you have a single photon input, and we consider the three waveguide circular array. So, so if you consider two waveguides, then it will be only linear. So the simplest structure that you can consider in this circularly coupled waveguide arrays will be a system of three waveguides. So first we consider example where we consider three waveguide circular array. And in this case, we are asking the question that if I start with a single photon state in the first waveguide, and whether it is possible to transfer it completely to the second and third wave. So here we have done the calculation and we have plotted the fidelity as a function of Jz. So Z is the distance that light propagates, and J is the coupling. So Jz is basically a normalized parameter. So we are asking this question that whether it is possible to transfer from first to second or third waveguide. So here, if you see these plots, if you see these plots, then we have only shown two plots here. So the red plot, it shows the evolution of fidelity in the first site, and the dotted black plot, it shows the fidelity in the second waveguide. And third waveguide we have not shown because these plots are same for second and third waveguide. So it's basically the same thing. Whether you consider the second or the third waveguide, you get the same plot for the fidelity. So if you look at this evolution of fidelity in the second waveguide, then what we find is that it starts from 0 and then it reaches some value, but it is less than 1. So this dotted curve, which represents the fidelity in the second waveguide, it never becomes equal to 1. So therefore, the single photon state is never perfectly transferred to the second or the third waveguide. So this is the situation for the three waveguide circular array. That is the simplest structure that one can consider here. And so we conclude that for the single photon input state, it is not possible to perfectly transfer the quantum state from the first to the second wave. So now let us consider so we have considered the 3 waveguides. Now let us consider the 4 waveguide circular array. So here again we are asking this question that we are starting with the single photon input state in the first side, and then we are looking at the evolution in the second and third side, and so the green plot, green dotted plot, it shows the evolution in the second waveguide, and this black and dotted black curve, it represents the evolution of fidelity in the third waveguide. So from these plots, we find that it is not possible to transfer the light from the first to the second side completely. So it is not possible to perfectly transfer the quantum state from the first side to the second side. So remember that the input is given to the first side. Since this green curve, it never becomes equal to 1. So therefore, we can conclude that the quantum state, the single photon state that we are considering here, is never perfectly transferred to the second side. Now let us look at the question whether this single photon state can be transferred to the third side or not. So if you look at, for this, you have to look at the black dashed curve. So if you look at the black dashed curve, then you find that the fidelity becomes 1. So in this case, at Az equal to pi by 2, the fidelity becomes 1. So therefore, we can conclude that the single photon quantum state can be transferred from the first to the third waveguide perfectly. So there is a perfect state transfer taking place for the 4th waveguide circular array. So here we are writing PST, that is a short form of perfect state transfer. So in this case, there is perfect state transfer of single photon state from the first to the third side. And this transfer occurs at Jz equal to pi by 2. Another thing that is important to notice here is that Z is the propagation distance and it is related to time. So either you can look at the evolution in terms of time or you can look at the evolution in terms of Z. It is equivalent because Z and E are proportional to each other and they are related quantities. So we confirm that there is perfect state transfer at Jz equal to pi by 2 in this 4 waveguide circular array. So in the previous slide, we have shown that for the 3 waveguide circular array, it is not possible to perfectly transfer the quantum state from the first side to the other sides. But here, it is possible to transfer the light from the first side to the third side completely. So there is perfect state transfer of single photon state for the 4 waveguide circular. So next thing one can look at is, so we ask the question that whether it is possible to transfer the to achieve perfect state transfer for the single photon input state again. So we are again starting with the single photon input state in the first side, and we are asking the question that whether it is possible to completely achieve quantum state, perfect state transfer for the case of 5 waveguide circular array. So again, if you look at these plots, so the red one represents the evolution of fidelity in the first side, and the black and the green curves, they represent the fidelity for the second and fourth. So they are equal. So that's why we have just drawn this, represented them by this black dash curve. And then third and fifth are represented by the green curve. So again, we see that this black and green curve, they never become equal to 1. So therefore, we can say that there is no perfect state transfer in the case of a 5 waveguide circular array. So, so next, one can also look at whether it is possible to do perfect state transfer for six waveguide circular array. So here we are plotting this. We are starting with the input in the first waveguide, and then we are looking at the possibility of the single photon state transfer to the other waveguide. So the blue curve, it represents the second and sixth waveguide. The green curve represents the third and fifth. So they are basically same. So we are writing we are just representing them by the same curves. And the fourth waveguide is represented by the black curve. So we find that again, the fidelity is never equal to 1. So in this case, again, for the 6 waveguide circular array, there is the complete transfer of quantum state doesn't take. So now we look at the example of another important non-classical state, that is a two-mode state, which is given by the noon state, and it is an example of a maximally entangled quantum state. And noon state finds important applications in quantum metrology and quantum sensing. In addition, they are also important for quantum communication. So what we want to study here is that whether it is possible to achieve the quantum state transfer or perfect state transfer for the noon state. So it has also been shown that it is possible to generate these noon states experimentally, at least for the small n values. So here, first of all, we look at the evolution of the photon number, the mean photon number that I had defined in the earlier slide. The red curve, it represents the mean photon number in the first waveguide. So we are giving the input. So we are considering a 4 waveguide circular array, and we are giving the input in the first 2 sites, and then we are looking at the evolution of this input state to the other sites. So here for the 4 waveguide circular array, we find that there is complete transfer of average photon number or mean photon number from the first site. So from the first 1 and 2 sites to the third and fourth site. So if you consider Jz equal to pi by 2, then there is complete transfer of mean photon number to the third and fourth site at Jz equal to pi by 2. So this mean photon number, it doesn't means that there is transfer of quantum state. So just by looking at the mean photon number, we cannot predict whether whether the noon state will be transferred from 1, 2 side to 3, 4 side. So we have to check other quantities, and here we consider the fidelity. We plot fidelity. So now we want to check that if I give the input in the 1, 2 site, then whether it is possible to transfer it to 3, 4 site. So we look at the plot for the fidelity versus distance z, Jz, and we find that the fidelity initially this red curve is the input side, the 2 input side, the first and the second sides, and we find that this fidelity decreases, and if you look at the this black curve, then it represents the fidelity for the transfer to the 3 and 4 mode. So we can see that the fidelity is becoming equal to 1 here. So therefore, we can say that it is possible to completely or perfectly transfer the mean photon number as well as the quantum state for the two-photon noon state in the case of 4 waveguide circular array. So next we consider whether it is possible to achieve the transfer of noon state in the case of 5 waveguides. So in the earlier slide, we have seen that it is possible to transfer the quantum state in the case of 4 waveguide circular arrays. Now we consider a 5 waveguide circular array, and we ask the question whether it is possible to perfectly transfer the noon state from, let's say, from first 1, 2 side to 3, 4 side. And so again, we look at the fidelity, and here we can see this black dash curve. It represents the fidelity for the transfer from 1, 2 to 3, 4 side, and we see that it is never equal to 1. So again, we can conclude that for the 5 waveguide circular array, it is not possible to perfectly transfer the noon state from the side 1 to 2. So in this case, the perfect state transfer doesn't take place for the noon state in the case of 5 waveguide circular array. We have also checked the possibility of perfect state transfer for the 6 waveguide circular array with the noon state input, and again we can see that the fidelity is not equal to 1. In fact, it is very much less than 1. So therefore, we can conclude that even for the 6 waveguide circular array, the possibility of perfect state transfer is not there for the noon state. So another important class of quantum state is the single mode squeezed state, and these squeezed states are very much important for application in quantum metrology and continuous variable quantum information processing. Also, they use squeeze states, and these squeeze states can be produced by the process of spontaneous parametric down conversion. So we look at the squeeze state input, and we ask the question that whether it is possible to transfer the average photon number and the squeezing from one side to the other. So here we define this squeezing parameters. Delta Qj and delta Pj are the fluctuations in Q and P quadratures, where Q and P quadratures for
क्या है उनके प्रोजेक्ट तो फिर मैं सबमिट है मुझे फेलोशिप प्लाटर में तो क्या बात है इतना इजी है क्या तक कराएं बाकी
Can you mute your Can you mute your Okay, so we consider these quadratures Qj and Pj, and J represents the mode. So if we are considering the first mode, then J will be equal to 1. If we are considering the second mode, then J will be equal to 2, and so on. So we are considering the squeezing in the Jth mode, and we are looking at the fluctuations. So if if the fluctuations in Q quadratures becomes less than half, then this SJQ will become negative, and we'll say that there is a squeezing in the Q quadrature. Similarly, if the fluctuations in P quadratures become less than half, then this quantity SJP will be negative, and therefore we can say that there is squeezing in the P quadrature. So we can calculate. So these are general definitions, and we can then calculate the expression for the squeezing parameter for our single mode squeeze state. So if you do this calculation, then you get this expression for the squeezing parameter. Sj is given by this expression. So AJL are the probability amplitude for the transfer of light from jth to the lth side. This Sj is written in terms of this AJL, and this negative sign. So you can see here there is a minus and plus sign here. So negative sign represents the expression for the squeezing factor in the P quadrature. Similarly, the positive sign represents the squeezing in the Q quadrature. And here R is the squeezing parameter or squeezing factor, and phi represents the orientation of squeezing ellipse. So if this quantity Sj, so this equation that we have written, it gives the expression for Sjp and Sjq, that is the squeezing factor for the P and Q, both the quadrature. So negative sign represents the P quadrature and positive sign represents the Q quadrature. And if Sjp or Sjq becomes less than 0, then we can say that there is a squeezing in the P or the Q quadrature. So let us consider the input state. So let us again consider the simplest system that you can consider in this configuration. So we have, if you consider the simplest case, that is the 3 waveguide circular array, then we consider the squeeze state input in the first site, and then we look at the possibility of transfer of squeezing to the second site and third site. So here we have plotted this. We have plotted this parameter that is squeezing in the Q quadrature for the first site and the third site. So first site is the input site. So we start with the squeeze state input in the first site, and then as you can see that there is a squeezing in the Q quadrature because it is negative here, and initially there is no squeezing in the other sides. But as time evolves, as time passes, then as light evolves, then we see that there is partial transfer of squeezing because this S2 Q becomes negative. So we can say that there is a partial transfer of squeezing from the first side to the second and the third side, and the second and third side both are same. So we have just drawn only one plot here that is given by this black dash curve. So this shows that there is partial transfer of squeezing, which is a non-classical feature from the first side to the second and third side. But there is no complete transfer. There is no perfect state transfer in this case. So the squeezed light is not perfectly transferred from the first to the second or the third side. But there is, we can see that there is a partial transfer of squeezing from the first to the second and the third side. So now we consider the 4 waveguide circular array. So after 3, we can consider 4 waveguide circular array. And in this case, we first look at the mean photon number, and we see that there is there is a complete transfer of mean photon number from first side to the third side. So third side is given by this black curve. So we can see that average photon number becomes 1 and Jz equal to pi by 2. So there is complete transfer of light from the first to the third side for the squeezed state input in 4 waveguide circular. As I have said that earlier, that it is not necessary that if there is transfer of the light from one, so in this case there is a perfect transfer of light from the first to the third side, it is not necessary that quantum state is also transferred. So for this, we can look at, so for considering the possibility of quantum state transfer, we can look at this quantity which is squeezing parameter. So here the black curve represents the red curve represents the squeezing in the first quadrature, and black curve. You can see that this becomes negative. Initially, it is negative. So we are starting with squeezing in the first waveguide, and then we can see that there is complete transfer of squeezing at this point to the third side. So in addition to the mean photon number, the squeezing, which is a non-classical feature, is also completely transferred from the first to the third side. So this is the case for the 4 waveguide circular array. So therefore, we can say that perfect state transfer take place, perfect state transfer and transfer of non-classical features take place completely for the case of 4 waveguide with the squeezed state. Now one can consider again the 5 waveguide circular array. So here also we can see that the initial side, the input side is the first waveguide, and then this other sides are given. So second side is represented by black curve, and third side is represented by blue curve. So you can see that there is a partial transfer of squeezing from first side to the third side. But there is no complete transfer of squeezing in the case of 5 waveguides. It is possible to have complete or perfect state transfer in 4 waveguide circular array, but not in 5 waveguide circular array. So one can also consider a 6 waveguide circular array, and here also we can see that. So we start with squeezing in the first side, and then we have plotted the squeezing in the third side. So we can see that there is a partial transfer of squeezing from the first to the third side because this S3 becomes negative. And however, the transfer is not complete. So we can say that there is partial transfer of non-classical features from the first side to the third side. But the perfect state transfer is not taking place. 6 waveguide circular. So having considered the single mode squeezed state, we now consider the 2 mode squeezed state, which is an example of entangled state. And 2 mode squeezed state have a property there that you have equal number of photons in 2 modes. And this is represented by this quantum state is represented by this equation. Here we know that in the case of 2 mode squeezed state, the squeezing is not in the individual quadratures. So the individual quadratures don't have reduced fluctuations. But if you consider the superposition of these modes, then there is a squeezing. So we consider this operator. So earlier, in case of single mode squeezed state, we had considered the individual quadratures for each mode, and we have shown that there is squeezing in these individual quadratures, for example, Q and T quadratures for the first side or second side or third side and so on. But here we are considering this quadrature operators, which involves the sides J and K both. And we know that the squeezing is in this superposition of these modes and not in individual modes for the case of two-mode squeeze state. So now let us consider this again the four waveguide circular array, and here we are considering the case where you have input in the first two sides. So remember that two-mode squeeze state is multi-mode input state. So we are considering the two-mode squeezed state, and we are looking at the photon number in the first two mode. That so the photon number in the first two mode are same, and they are represented by this red curve, red block, and so we can say that this we are starting with light in the first two modes. So that's why this value is 1. And as light propagates, there is a complete transfer of the mean photon number from the first 1-2 side to the 3-4 side. And because this black curve represents the average photon number in the third and the fourth sides, which because the average photon number in the third and fourth sides are same, so we are just representing it by the same plot. So here we can say that this average photon number is becoming 1. So therefore, therefore there is complete transfer of average photon number from the first 1-2 side to 3-4. So the next thing that we look at is the transfer of squeezing for the 4 waveguide circular array, and we consider the squeezing parameter that we have defined. And if this value becomes negative, then there is squeezing in the joint quadrature. So here initially the squeezing is in the 1 and 2 quadrature, and as light propagates, there is complete transfer of squeezing from the 1-2 side to the 3-4 side. Because if you see this value at this point, it is exactly same as the initial value. So there is complete transfer of squeezing from the first and second side to the third and fourth side of the array. And so this is the case for the 4 waveguide arrays. And in this case, we can say that the perfect state transfer is taking place for the 2-mode squeeze state as well, when we consider the 4 waveguide. So next thing one can look at is the case of 5 waveguide circular array. So here also there is a partial transfer of squeezing. So here this value is negative, and then S34, if you look at S34, then there is a partial transfer of squeezing because these values are becoming negative, but the complete transfer of squeezing doesn't take place again in the 5 waveguide. Okay. So the next thing that one can look at is this example of the 6 waveguide circular array. So here also we can see that there is partial transfer of squeezing to the third and fourth sides, and so this value becomes negative. So even though there is partial transfer of squeezing, which is a non-classical feature, but it is not possible to completely transfer the 2-mode squeezed state from the 1-2 side to the 3-4 side. So having considered all these non-classical states of light, we also wanted to check what will happen if we have a coherent state. So if you have a coherent state that I had already written the form of the coherent state. So if you have a coherent state and you look at the possibility of the transfer of mean photon number in the 4 waveguide circular array, then you find that if you look at this average mean photon number, then we see that the mean photon number is getting transferred from the first side to the third side, and the transfer is complete. So the mean photon number is completely transferred from the first side to the third side, and there is some transfer of light to the second waveguide as well. So this is the case for the 4 waveguide circular array. So the question that we can ask is whether this complete transfer of average photon number in the case of 4 waveguide circular array means that the coherent state is also completely transferred or not. So as I said, that it is not necessary that if the light is completely transferred, it doesn't indicates that it is possible to completely transfer the quantum state. So for the transfer of quantum state, we again look at the fidelity. So here we have done the plot for the fidelity for the first waveguide and the third waveguide, and you can see that the fidelity of state transfer from the first to the third waveguide at Jz equal to pi by 2, where the complete transfer of average photon number is taking place. At that point, the state is not completely transferred because this fidelity is equal to this value, which is not equal to 1. And in this plot also, you can see that the fidelity is not equal to 1 at any value of z. So the coherent state is never completely transformed from the first side to the third side. And so even though there is complete transfer of average photon number for the 4 side, in the case of coherent state, the quantum state itself is never perfectly transferred from the first side to the third. So to conclude, we have studied the quantum state transfer for the circularly coupled waveguide arrays, which are important for the application switching and coherent transfer of light. What we find is that for the 4 waveguide arrays, the perfect quantum state transfer as well as the transfer of average photon number take place for all these non-classical states, such as single-photon Fock state, two-photon Moon state, and squeezed state, single-mode squeezed state, and the two-mode squeezed state. However, the perfect transfer of coherent state is not possible. Perfect state transfer of coherent state, the mean photon number is getting transferred in the case of coherent state also, but the perfect state transfer for the coherent state is not possible in the case of these circularly waveguide arrays, circularly coupled waveguide arrays. In addition to that, we also find that there is partial transfer of squeezing from the input side to the other side for the case of 3, 5, and 6 waveguide arrays. So with this, I would like to conclude my talk, and I would like to thank all the collaborators, the students who have contributed to this work. And I would also like to thank the SCRD, which is a funding agency, who have funded this work, and this work was not possible without their support. I would like to thank them. And again, I would like to thank Professor Amit Rai for arranging such a nice conference and inviting me to present my work. So thank you everyone for your attention, and if there are questions, then I'll be happy to take them.
Thank you very much, Dr. Rai. I think the chat box has some questions.
There are some.
No, I think. Well, there is one that says, how does quantum state transfer help in quantum communication?
So quantum state transfer is used. So one thing is that you can use quantum state transfer. Obviously, this quantum, you want to transfer some, in quantum communication, you want to transfer quantum information from one point to another. So with this, so you can do it using the using this kind of perfect state transfer schemes. In addition to that, this quantum state transfer is also helpful in quantum computation, where you connect the nodes, you connect different nodes. That's, for example, in classical computers also you connect different nodes. So for the quantum computers also you need to connect these different nodes, and then you want to transfer the information from one place to another. This kind of quantum state transfer is helpful there. And quantum communication, it involves the transfer of quantum states. So quantum state transfer schemes, they are helpful in quantum communication.
There is a question for the 4 waveguide circular array. It is astounding that there can be a perfect transfer from first to third waveguide, even when we have nearest neighbor coupling, which means that 1 and 3 are not directly connected. Am I right? That is the question that has been put on.
Yes, 1 and 3 are not directly connected. In fact, we have drawn this. So if you look at this, so we wanted to consider whether it is possible to transfer the quantum state from the first side to, so in this figure we have drawn this first side to the fifth side, but they are not directly connected. So yes, this for 4 waveguide array, these first and third sides are not directly connected, but it is possible to transfer from first to third side.
Okay, there is a question. What sets the limit on n, capital N?
N is the waveguides, the total number of waveguides. Yes, N is the total number of waveguides. So if you see this figure, then this R is the radius of this circle. It is related to this circumference. So if you do this calculation, then you will find that there is a upper limit to the total number of waveguides that are possible, because this R is related to the circumference. So you can put, so you're putting these sides on this circumference, which is related to this R. So you cannot put any number of sides. So there is some limitation on the number of sides that you can have, but 5, 6 you can easily.
I just want clarification.
Yes.
The number of waveguides are symmetrically placed, right, on the circular array?
Yes, yes.
There is no asymmetry in this whole thing.
Yeah, we have not considered, yes.
I don't see any questions in the chat box. Is there anyone who wants to use the mic and ask a question? I don't think there are further questions. If you have any questions, you can raise your hand. Abhinav Dhawan raised hand. So are you going to put it in the chat box, or are you going to ask the question? Okay, go
hello,
on.
sir. So
Yes,
I
yes.
wanted to ask, what sort of coupling do we have between the waveguides? Like, how do we get the coupling?
Means you are asking about the value, or you are saying how we couple?
No. How do we, like, experimentally, if we want to couple the waveguides, how do we do that?
Yes. So what you do is that you have to bring these waveguides close to each other. If they are very far, then there is no coupling. As you bring them close to each other, because these modes are not completely confined. So so if you consider any individual waveguide, then the mode is not completely confined. So when you bring these 2 waveguides, let's say, close to each other, then these modes will start overlapping. And because of this overlapping, there is coupling between the sides. But when you break, so what you need to do is you need to bring them close to each other, and then you can have the coupling.
Okay, sir. Thank you.
Maybe I'll just go with one more question. I would like to ask if you know of any experimental group who's working on this, or if people started working.
There are a lot of groups working on optical waveguide arrays. So there are many people working. So for example, there is a group in Bristol where they are working with these optical waveguides. But mostly they have worked on this linear arrays. So there is a group by Bristol, and then there are a couple of groups in Europe also. They are working on these experiments.
Okay, thank you.
Is there anyone else? You can raise your hand. Okay, I don't see anything more in the chat box, nor do I see anyone raise their hand. I'm just curious. May I ask you something before we wind up?
Yeah, yes.
Yeah, because you know that Professor Agarwal, Srinivasan, Mehta, Shanta, Chaturvedi, they all got together and wrote this very nice PRL paper many, many years ago on multi-photon coherent states, where they have said that the even coherent state is the Janus-phased partner of the single mode squeezed vacuum, and the odd coherent state is the Janus-phased partner of the, I think, the UN state. The thing is, I'm just wondering if you worked instead of the single mode squeezed vacuum, if you started with your input state as the even coherent state, because they are related through the algebra, what kind of results you would see, and if you can sense some similarities. That's just a comment.
Yeah, we can check that. That would be surely interesting. But we have not checked yet, so we would like to check. It will be interesting.
Okay, thank you very much.
And
In the absence of any further questions, I call this discussion to a close. I want to thank Dr. Amit Rai for a very clear and almost tutorial-like session where he has taken everybody through the various steps. Thank you very much.
thank you. Thank you.
Perhaps you can stop screen sharing.
Yeah.